Hello everyone. Today I'm going to talk about how spatial dynamic subspace can quantify network dynamic integration and segregation, detect schizophrenia effect, including sex-specific one, and capture the complex relationship of dynamic information to multifactorial genomic data. I have nothing to disclose. In general, the primary objective of functional connectivity study is to evaluate how interaction and communication occurs across the brain. Essentially, our aim is to evaluate functional interaction among functional units. Sometimes we call them functional source or functional entities. Therefore, our understanding of brain function depends on how well we estimate functional sources and their interaction. A functional source can be defined in lay term as a region with similar functionality and can be characterized by two elements. It's a spatial pattern that characterizes its distribution in a space, and temporal pattern that describes its activity over time. And of course, functional sources can have different size from large scale spatially distributed to especially granular one. Many studies have used anatomical fixed or subject-specific spatially static node to approximate functional unit, and therefore they implicitly assume that spatial pattern of functional sources remain constant over time. Yet the brain is highly dynamic, and the spatial pattern of sources can change over time as demonstrated by recent study. For instance, recent studies have shown that different brain regions, in fact, can contribute to a given network at different points in time. Here we can see three states of the default mode network showing in the RGB additive color. We can see posterior cingulate and precuneus region are in white, meaning they contribute to the default mode network in all three states, which is not surprising as they are the primary parts of the default mode. But we can see the thalamus is in red, meaning it contributes only in one of the states, which can potentially explain the inconsistency we see in previous static analysis. Some reported the thalamus as a part of default mode, some did not. Here we see thalamus is the part of default mode, but only in a specific dynamic state, in a specific point in time. In addition, spatial dynamic analysis have shown that brain networks spatially integrate and segregate from each other, reflecting the dynamic interplay between integrative process and specialized intrinsic activity. For instance, as you can see in here, the spatial dynamic analysis can identify the transient emergence of cerebral and visual network within other networks. All of these findings call for further investigation of spatial dynamic. Yet, given the lack of prior knowledge of the spatial pattern of functional sources and their variation over time, the data-driven approach are primary or essential tools to estimate the functional sources from the data itself, because as I said, we don't have a prior knowledge. But there are several factors that hindering progress toward this goal, such as, for example, low signal-to-noise ratio of the resting state of fMRI, or limited information in the short segment of time, or uncertainty in identifying the corresponding network within and between subject. Here, inspired by the group inference framework, we introduce a time-resolved reference-informed network estimation technique to capture time-varying spatial networks. First, we run a group-level spatial independent component analysis, ICA, to obtain a group-level network. In the next step, the common pattern, as you can see in the panel B left side, is to use a group-level network or group-level networks as a reference to estimate corresponding networks for each subject, using approach like spatial constraint ICA. Here, what we suggest shows in the panel B right side, which is combining sliding window technique with a spatial constraint IC approach that is capable of capturing network from short time segment to estimate time-resolved network. We use a multi-objective optimization IC with reference, or MU-ICR, as our recent study showed it can effectively capture large-scale network from short or limited data lengths. We use this framework to evaluate how a large-scale network dynamically integrate and segregate from each other. We calculate the spatial covariance at each time window to estimate the time-resolved spatial functional network connectivity, which is an estimate of network spatial coupling. And next, we apply the k-mean classing on these window spatial functional network connectivity matrices to obtain the covering spatial dynamic states. Panel A here showing the composite view of the 14 large-scale network we identify, each network thresholded at the z-score of 1.96 and presenting different color. For spatial dynamic state was determined using the elbow method, which are presented in the panel C. Next, we use a spatial dynamic state to investigate schizophrenia-related alterations in the dynamic spatial coupling, or in the changes in the dynamic spatial integration and segregation. We run a statistical comparison for each spatial functional network connectivity pair using the GLM model with age, sex, mean frames-wise displacement, and site as a confounding factor. Those cells in the panel A with asterisk represent the pairs with the p-value less than 0.05, and panel B show the connectogram of the pairs with significant diagnosis or interaction 6 diagnostic effect after FDR correction. We also evaluate the genomic predisposition of spatial functional network connectivity pair with a significant schizophrenia effect using the polygenic risk score of the schizophrenia. We observe two pairs show a significant correlation with the PRS for schizophrenia after FDR correction, including the default mode salience pair in state 1, which also shows sex-specific schizophrenia effect, and temporal and primary motor pair in state 2, which also have a significant diagnostic effect. And next, we investigate how schizophrenia-related alteration that we saw in the low-dimensional spatial dynamic states linked to diagnostic differences in voxel space. We focus on a network that involve in those two pairs with both significant schizophrenia effect and genomic association. We perform a voxel-wide statistical comparison while controlling for the same confounding factor. Panel A shows the result of the spatial similarity between beta spatial map of variable of interest like diagnosis or interaction and the network map. We can see, for instance, for the salience beta map has a significant similarity with the default mode, which for both interaction and male diagnostic effect. Panel B and C show the whole brain beta map and the region with significant diagnostic or interaction effect. We can see, for instance, the region with significant effect for the salience are those that commonly associated with the default mode, including posterior cingulate cortex and precuneus. And in fact, we often mask out these regions in previous analyses due to their low contribution to the salience network, which highlight the importance of these weak functional connectivity to detect the nuance alteration. To sum up, we introduce an approach capable of capturing network spatial dynamic. We observe that brain system dynamic can be captured by dynamic spatial functional network connectivity, a low dimensional representation of system-wide spatial dependence. The approach detects this disruption in schizophrenia, including sex-specific differences. The approach shows the potential in capturing nuanced relationship between dynamic information and genomic data, and also result underscore the potential of the weak functional connectivity in clinical landscape. Thank you for your time.